good morning everyone. We are group 6 and our members are Cheng, Emran, Nur Adibah and Teeab Tahzib. And today we're going to present about a connecting rod. Okay, so first question that we have to ask is, where are connecting rods used and why do we use connecting rods? So let's dive right into the presentation and we can get the answers. So first of all, connecting rods, as the name suggests, is used to connect. First of all, it is used in internal combustion engines in order to connect a crankshaft with the pistons. And what does it do? Basically, it converts the reciprocating motion into rotating motion. So the next question that comes is, why do we need to do finite element analysis of connecting rod? So first of all, we have to understand that if you have a bad quality connecting rod without much analysis, then it will fail. The reason it fails is because the connecting rod is always under a tremendous amount of stress. This is because it's sometimes being pulled, sometimes it's being pushed, and so what happens is it's actually always it's being stretched and it's also being compressed. So when the car is driving at very high speeds, obviously the amount of stresses goes on very high on the connecting rod. So unless we have a very good finite element analysis to understand how much which material to use and whether it will fail or not, there's a high chance that it will fail. That's why as engineers we need to analyze. And whenever a connecting rod fails, the bigger problem that appears is that bits and pieces can actually fall off. As you can see how it has failed, the pieces are falling off. And these pieces can actually enter into through the crankcase of the engine, and if that happens, the whole engine actually goes down. So next, Emran will actually talk into more detail as to why connecting rod is chosen. Emran.
Okay, my name is Nur Adibah Abu Mansor. I will explain why we choose connecting rod. First, connecting rod is a critical component of internal combustion engine. Without connecting rod, the engine will not work. Second, connecting rod is a linkage that converts reciprocating motion into rotary motion. Third, repetition of tensile and compressible load on every stroke. When tensile and compressible is affecting the connecting rod, it may break due to fatigue stress. Fourth, length of strokes to which size is very important to avoid buckling failure. I will explain. Next is objective. Firstly, obtain model analysis of connecting rod under different loadings corresponding to crank angle. This is to determine stress and displacement of connecting rod under loads ranging from tensile load. Second is applying mesh analysis under different number of mesh elements to know how different number of elements will affect the accuracy of stress value until certain value of mesh, and the accuracy will converge.
Hi, I am Anita. Today I will present about the boundary conditions. Okay, this is the connecting rod. So the end of the connecting rod is connected to the piston, while the big end of the connecting rod is connected to the crankshaft. So basically, at the small end of the connecting rod will occur some deformation because the force exerted is on Z and X directions. After we do some analysis, we obtain that at 0 degree of the angle, the normal force is 0 kN and the axial force is 8 kN. At 30 degree, we obtain the normal force is 3.17 kN and the axial force is 16.2 kN. While at the 90 degree, we obtain the result is 1.36 kN and the axial force is 3.26 kN. So the material properties is AISI 434 steel. So we choose the material properties because it is available at the Finite time. We choose the load at 30 degree crank angle because it has the critical forces. So at the Finite time we insert the value at Fx is 3.17 kN and at the Fz is 16.2 kN. While at the y-axis there is no forces acting. So we choose the constant as fixed at the big end of the connecting rod. This is the example of the material properties. So from the material properties, we get the Young modulus, shear modulus, and also all the data in units TSI.
My name is Cheng Vay Vern, so I'll proceed with the meshing and results. By using connecting rod is analysis using Finite Element Methods software. So for our first initial meshing that we did, we actually meshed it to a very small mesh size, as you can see from this, which is very small. But when we obtain this very small mesh size, we are unable to further analysis by running loads and constraint, which results in this fatal error. This is because the element quality is not good enough, and for when mesh quality of Jacobian is more than 0.95, we cannot proceed with our analysis. So we found a solution which is by using mesh size of 0.3, 0.4, 0.5 and 0.6. The following result is the Warman stress occurring at the connecting rod at this 30 angle crank angle at the following load that's been presented by one of our members. As you can see from this result, the critical part of this stress actually occurs at the shank of this connecting rod, which is around this area. And you can see the difference from mesh size 0.3 and 0.4, both also this critical part is about the same place. Also, the mesh size of 0.5 and 0.6, where the critical 1 meter stress also occurs at this shank line. About the total displacement, you can see that it actually happens at the end of the piston end, which actually moves the total displacement actually is the maximum about this area, showing that and for mesh size 0.3, 0.4, and also 0.5 and 0.6. But actually from this result, you can see that the displacement is actually a lot due to the force, but this is because the material property that we use in VMAT is not actually the material properties that is actually used in this industry. We just the exposure that how this force that actually affects the connecting rod. And as you can see from the mesh size, and when you compare the result between the mesh size of the 1 meter stress and the total displacement, you can actually see that the error at critical is actually very small, which actually shows that our value actually converges at this mesh size.
So we have actually been talking about a wonderful mesh analysis from Cheng so far. But I want to take the analysis to the next level by extending the post-processing level. So let's dive right into it and see what results we get. So first of all, in Teeab Tahzib, you can actually not only get the post-processing in terms of colors, but you can also get it in quantitative units. For example, here we can see the summary of all the different outputs that you can generate through analysis. One of such outputs that we're interested in is total translation. So you can see in the table that there are a few columns, and one of the columns says the title, which is total translation. Mean ID actually refers to that particular element which has the least amount of total translation, which is obviously 0 in this particular case. And max ID refers to the ID of the element which has the maximum amount of total translation, which is around 0.196. Another output we're very interested in is the solid von Mises stress. For this, we actually can see that the maximum von Mises stress is on the element ID 9324, and it's about 358,727 psi. Moving on, we would like to know actually where is the element where the maximum amount of von Mises stress falls upon. As Cheng has already talked about, it's somewhere along the shank, and it should be somewhere along the red zone. And upon further analysis, it's exactly right in somewhere along the red zone. But you can see that when I highlight the element, which is the maximum value for a von Mises stress, it comes out exactly somewhere over there. What this tells us is that that is the particular element where you can expect the maximum von Mises stress to exist in this particular load and constraint conditions for this particular connecting rod. But if we actually make the element smaller and if we had a finer mesh, then we would obviously be able to pinpoint more finely that particular location where we can expect the maximum von Mises stress to exist. Another element that I want to talk about is you can look at the diagram that I've shown you before of the connecting rod that's slowly broken apart. You can see one of the regions where it actually cracked is the shank region. So it somehow verifies our analysis that this particular part might have one of the maximum amount of von Mises stresses. So then, when we actually want to know more about how the von Mises stress varies along a line, we can actually select a particular surface, or we can cut a plane and then select a particular line of elements and see how the von Mises stress varies along the line. So what I have done over here is that I've selected the surface on the outside and I've actually gotten a few points along a particular line. And you can see that I have put the element ID and the amount of von Mises stress that that particular element at that location feels. So you can see that starting from the left, we have the ID, element ID 10,294. It has a von Mises stress of 20,546 psi. Moving on, we can see the von Mises stress is rising. From 20,000 it goes to 168,000, then comes to 214,000, and then it rises to the maximum, which is 241,000, and then it starts falling again. So it sort of goes with the post-processing data that you see, and if you actually put a graph on those elements that you've selected from the left, and if you look at the stress that they undergo, we can see the graph is slowly rising, going at a peak and then slowly coming down, which actually verifies the post-processing data that we've seen before, that the von Mises stress is varying and then it's highest at the shank level. Now, I wanted to actually delve further into the total translation. This is very interesting because you can see that when we do the post-processing for total translation, as Cheng has earlier mentioned, it's supposed to be somewhere along the tail of the connecting rod. However, when I wanted Teeab Tahzib to show me that particular element where the maximum total translation happens, actually it's not the tail. It's that particular element you can see somewhere if you go slightly inside the connecting rod rather than the tail. So you can see that I can use Teeab Tahzib to show me the exact element which is having the maximum total translation, and that element ID is 9,944 and the maximum value is 0.196. So if we move on, then we can actually show that the result is correct, because I have then used element picking ability to actually pick some elements along the tail, and you can see that along the tail the maximum total translation is around 0.186, 0.189, 0.189. It does not cross our maximum value of 0.196. So what does this tell us? It just tells us that sometimes the contouring, the colors might not be enough. We need to actually go beyond that, because looks can be deceiving, and it's a job of a wise Finite Element analyzer to actually move beyond simple processing and to go into extended processing to actually find out that particular element or those particular regions which are really undergoing the maximum displacements or the maximum amount of von Mises stress. Only then we can create a very good analysis and we can create devices which do not fail under lots of tension and compression. I hope this presentation has enlightened you about Finite Element and how we can analyze using the software and how it does give us very good results in terms of creating practical devices in real life. Thank you.